Here we're going to continue looking at how do we recursively develop these polynomials and these Lagrange polynomials. And this is the form that we are hoping to get. So we're hoping to say our next Lagrange polynomial, when we add one more node, is our previous Lagrange polynomial times x minus the new node plus some other business. And so we need to think about what is that other business. And our next theorem is going to address that for us. And so if we have our function f is defined at x0 up through xk, and x sub I and x sub j are two distinct points in the set, then that Lagrange polynomial, it can be expressed as x minus one of those points, so let's say x minus x sub j, times the Lagrange polynomial that has 0, 1, node 0, node 1, all the way up through node j minus 1. It does not include node j. It jumps node j and goes j plus 1 up through node k. So we have that polynomial times x minus xj minus x minus the other node, x minus x sub I, times the Lagrange polynomial that skips over I. So I minus 1, I plus 1, through k. And all of that's going to be divided by x sub I minus x sub j. So the order in which this difference occurs is exactly opposite. And so that is what the Taylor polynomial, the Lagrange polynomial is. Right? We can represent it in this way, where we can describe this Lagrange polynomial that uses all of these nodes as a Lagrange polynomial using one fewer node times this, minus a different Lagrange polynomial that uses one fewer node. And that interpolates it. Right? How does that interpolate it, or how can we be certain that that is equal? Well, let's think about what happens to this Lagrange polynomial at x sub I. Right? So if we plug in x sub I, what's going to happen? Well, for this piece right here, we're going to have 0 in this part. And so this piece will completely go away. And so we're left with x sub I minus x sub j. Oh, but that's exactly what's in the denominator here, plus the polynomial evaluated at x sub I. Right? This Lagrange polynomial. Right? So that is ultimately equal to p0, 1, up through j minus 1, j plus 1, up through k. But since this is a Lagrange polynomial, that Lagrange polynomial, it should agree at x sub I. Should agree with the function. So this should be equal to f of x sub I. And we have something similar, although slightly different, that happens when we evaluate at x sub j. Right? So when we plug in x sub j, then this term is going to go to 0, which means that whole first term goes away. We will have x sub j minus x sub I, but that is being multiplied by a negative, and so this and this will cancel, just leaving us with p 0, 1 up through I minus 1, I plus 1, k of x sub j. And since that was a Lagrange polynomial, and this is a node that was used in that Lagrange polynomial, it should agree with our function. And that should be true no matter what choice of I and j we make. It should agree at those points. And so what we're going to do is we're going to build something out kind of like this. Now we're going to build those out in a more methodical fashion, not just choosing random nodes in the middle that we're tacking on. And so we're going to add a little bit of more notation. There's a lot of subscript stuff here that's going on. And so let's have this new notation. Let Qij be the Lagrange polynomial that ends at I, right? So the last subscript that's going to be used is I, the last index is going to be I, and it's going to start j units ahead of I. So it's going to go from I minus j all the way up through I. That way we don't have to write a whole bunch of these things. And so our methodology is going to be this. We have P0 and P1. In terms of Q's, these would look like Q00, Q01, Q02, Q03, and Q04. Right? Because we are ending at 0 and we started 0 units ahead, we only used the single node here. Now, if we combine these two, when we combine those, we should end up with a Taylor polynomial. Nope, not Taylor. A Lagrange polynomial that's using nodes 0 and 1. We could say that that is the Lagrange polynomial that ends at 1 and started 1 unit prior to 1. If we combined these two, it would be the Lagrange polynomial that uses nodes 1 and 2. So it ends at 2 and started exactly 1 unit ahead of it, 1 index ahead of that. The Lagrange polynomial that makes use of x2 and x3. So it ends at 3 and started exactly 1 ahead of it. And then P3, 4. It ends at 4. And I've written all of these backwards. Oh, man. So all of them, including the first one, I said what it ends at, but I wrote that second instead of writing it first. So this one ends at 4 and starts 1 unit ahead of it. This ends at 3, starts 1 ahead. Ends at 2, starts 1 ahead. Ends at 1, starts 1 ahead. This ended at 0 and started 0 ahead, ended at 1 and started 0 ahead. 2, 0, 3, 0, 4, 0. And then we could take those Lagrange polynomials here, right, that are all second degree Lagrange polynomials, and we can combine them in this way. So when we combine these polynomials, we have a polynomial that now is taking into account the points 0, 1, and 2, which we could call it's ending at 2, and it is starting 2 ahead of 2. This one is P1, 2, 3. It ends at 3 and starts 2 ahead of it. It ends at 4 and starts 2 ahead of it. But wait, there's more. So this is the Lagrange polynomial using nodes 0, 1, 2, and 3, which is Q. It's ending at 3, and it's starting 3 ahead of it. This one ends at 4 and starts also 3 ahead of it, starts at 1. And then we can finally combine these two. So the Lagrange polynomial that has 0, 1, 2, 3, and 4 is Q4. 4. Ends at 4, starts at 0, starts 4 ahead of 4. So that's the polynomial. In our next video, we will take a look at an example of this.